we're on our third discussion of Chapter 4. You have looked at force causing acceleration and friction. We're now going to look at mass and weight. All right. Really important that you don't use these terms interchangeably. In physics, in all of science, these mean very, very different things. Let's look at the definitions that you need to remember. When we talk about mass, we mostly are talking about the amount of stuff that's in our object. And an easy way to remember this is the massiveness or the sluggishness, the amount, the level to which the object resists movement or change in its state of motion. Just think mass as being massive. By contrast, weight is a force related to gravity. Now, is weight related to the mass? Absolutely. Are they the same thing? Not quite. One of the big differences is that weight, we're always going to look at as a vector. It's going to have a direction of some it's going to have some direction or another, whereas mass is a scalar quantity. We had asked before, when do the scalars come in? Mass is an important scalar quantity. Let's talk about that some more. A mass is the measure of inertia of an object. Doesn't matter if gravity is involved. A more massive object is more massive in any situation. Suppose I've got two boulders in my front yard. One's about the size of our bowling ball, the other's about the size of a car. The bigger one has more mass. It is more massive. If I need to roll them across my yard, the enormous one is going to be much more resistant to that motion. The smaller one is less so. When we talk about mass, the unit of measure is kilogram or grams in the SI system, and always when we are talking in physics, we want to be using the value of kilograms and grams. Weight, in contrast, is the force of an object due to gravity. All right. Now, my two big boulders in my yard, the bigger one does also weigh more than the smaller one. We measure this in newtons because that's a measure of force. Oddly enough, 1 newton is about the force that a good-sized apple has in your hand. In British units, the unit of force is a pound, which is one of the reasons why we think about pounds and weight in everyday language. Okay, think about the two boulders in my yard again. If I take one of those objects and half the mass of it, and then go and weigh one of those pieces, is the weight of the object halved? Is the weight doubled? Does it depend on the location? Or none of the above? All right, what do you think? Well, I would have written this question a little bit differently. The weight of the object is halved so long as we are weighing them in the same place. So long as we've stayed in my front yard to weigh the full boulder versus the half boulder, then the weight will be halved. If we were to, well, let's just leave it at that. So weight and mass are directly proportional to each other. Okay? And they are directly proportional. So as one goes up, the other one also goes up. There's our anvil that we had in an earlier chapter in one of the videos that didn't make a whole lot of sense then. It's going to make some more sense now. Um, we talked about in everyday conversation, you could use weight and mass interchangeably. They mean about the same thing when we're talking everyday language. Uh, in scientific language, mass is a little bit more fundamental. It's a little bit more basic than the idea of weight. Mass is what it is. And the big thing to remember it is if we were to take our boulder or this anvil, if we were to drag it up to the moon, the object doesn't change. The massiveness of it doesn't change if we're on the Earth or the moon or in outer space. The mass stays the same. Okay? But the weight of the object, if we were to weigh it on the moon, because the moon has a different gravity, it's going to push against our scale into a lesser amount. So the weight is different on the moon than it is on the Earth. Okay? Mass stays the same because the object stays the same. Weight changes because the environment is different. Are you confused yet? This is a tough one. 1 kilogram, this is one of the reasons why we like SI units. 1 kilogram weighs about 10 newtons, exactly 9.8 newtons. Do you remember where we've seen that? And it is in relationship to the force of gravity. If you need to go back and forth between the two, a kilogram is about 2.5 pounds, and a pound is not quite 5 newtons. It's a little bit crazy arithmetic to go back and forth between those. We can if we have to. I just as soon avoid it. All right. This is a problem that you saw earlier in one of the earlier chapters, that we are hanging a heavy ball using 2 pieces of string. And the string above the ball and the string below the ball are from the same spool, so they are the same strength, the same thickness, they are the same kind of string. We've just elected to hang some above and below the ball. Here's the question. If I take the bottom string and pull down slowly, and I keep pulling, I keep increasing the downward force until one of the strings breaks, it's going to be the top string that breaks. What is that illustrating? What is that telling us about the situation? Does the fact that the top string breaks, does that illustrate the weight of the ball? The mass of the ball? The volume of the ball? Or the density of the ball? Why is it that the top string breaks? Well, the top string breaks because of the weight of the ball. And when we have the ball and the force of you pulling down on it, the top string feels both the force that you're pulling down and the weight of the ball. Okay, the bottom string is only feeling the force that you're pulling down. Let's look at the opposite. What in this case we pull down with a jerk, like we're tearing off a paper towel? In this case, if you pull quickly in a jerking motion, you will break the bottom string. We so have to do this in class. Why is it that the bottom string breaks? Is it because of the weight of the ball, the mass of the ball, the volume of the ball, or the density of the ball? Why is it that when we jerk, it's the string on the bottom that breaks? Well, in this case, it's the mass of the ball, because when we pull down with a jerk, The ball is resisting. It doesn't want to move. It is resisting motion. So the force is just acting on the bottom string. It's the laziness of the ball that keeps it at rest. It's your massiveness that resists acceleration. All right? Think about those two big boulders in my yard. If I push them with an equivalent force, the smaller one is going to move quicker. As another example, if one mass is 3 times larger than another, then an equivalent force is going to give you 1/3 the acceleration. So they are inversely proportional. As our mass increases, our acceleration decreases. Let's work with that a little bit more. And we will do that on our next video.